now we can start with chapter 2 as a new chapter, relations. Do you hear me, dear friend? Okay, you can see the shared page, right? Okay, so as a relation, we can talk about many approximation considering the set theory. Starting with that chapter, let's start the main definition from your book. We know some relation like less than, right? Is parallel to, is subset of, and so on. We saw like contains and so on. We saw some kind of relation. These relations consider the existence or non-existence of a certain connection between pairs. So there is the pairs of objects taken in a definite order, formally we define a relation in terms of these ordered pair. So there's a relation, and in that relation we have some pairs, and according to that relation we will say there is some ordered pairs. And what else? And ordered pair of elements like A and B, where they are, A is designated as the first element, and B as the second element. Is denoted, we will show that pair by in parentheses A and B, And we can say also, if there is the two pair like A and B pair, there is the equalities between C and D pairs, and we can say if and only if A is equal C and B is equal D. And what else? So, for example, of course, you get the idea. For example, A B pair is not is equal B A pair. So we can say unless A is equal B, otherwise we can say something like that. So new title is a product sets. Product sets. We have two arbitrary sets. Two arbitrary sets like A and B. A and B. The set of all ordered pairs like A and B parentheses. So these are, A is the element of set A and B element is set B is called the product. So we are defining the a relation as a product set. We have to first define the product, or we can say for the product Cartesian product of A and B. So this is also a relation with that two set, a short designation of this product is a, like the multiplication symbol or X symbol, B, which is read A cross B as a definition. We can say A cross B is equal, there is the AB pair. A is element of set B, set A, and B is element of set B. if we have, okay, let's say this is the page 1. If we have, product relation for only set A, at that time, okay, let's say this is the page 2. If we want to write A square, it means there is the A cross A. Okay, let's write example. Simple something. Example. Okay, we have set A, let A is equal 1 and 2, and there is the B set, and inside of the B, A, B, and C. So A cross B, okay, let's say A cross B, we have, relation A to B. We need some pairs like 1 to A. We have 1 to A. This is a member of A cross B. And let's say 1 to B, I'm writing the same example from your book, but you can do something as a different if you want. 1 to C, and there's the 2A and 2B and 2C pairs in that, A product B. And we can write B product A also. We are writing the all pairs, and A to 1 is the first pair, A to 2, and B to 1, B to 2, and C to 1, and C to 2 is the last one, C to 2 is the last pair. If we want, we can write, A to A as a product pairs. I will write 1 to 1. 1 will go to 1 as a first pair. 1 to 2. And then 2 goes to 1. And 2 goes to 2 as A to A. If you want to write as a B cross B, I can write A to A, of course, A to A as a first pair, A to B, A to C, then B to A, B to B, and B to C, and C to A, C to B, and last one, C to C as the last pair. So this is the, B square, and that one is also A square. So we saw, A cross B, B cross A as a product set for, considering the D sets A and B. And what we have as a next, so first of all, as you see, we can say A cross B is equal B cross A. The Cartesian product deals with ordered pairs. So naturally, the order in which the sets are considered is important. So we can say also number of elements for that, product A, product B is equal, there's the 2 times 3, 2 times 3. This is also is equal, or we can say something is like, number of element A times number of element B. So this is equal 2 times 3. Totally we will have as a pairs as a 6 in that product. In fact, of course, we can say that, explanation, if there is the A product B numbers, number of A times number of B for any finite sets, right? For A and B. And the idea of a product of sets can be extended to any finite number of sets for any sets like A1, A2, and so on. There is the AN. The set of all ordered and tuples A1, A2, and AN, where A1 is the element of A1 or member. A2, small letter A2 is element of capital letter A2 set, and so on. AN is the element of AN is called the product of the sets A1 A1 to AN and is denoted or represented by A1 cross A2 cross AN, or we can write, multiplication symbol as a pi I is equal 1 to N AI. Any question? So we saw some relation, and especially we saw relation as a product, and we write A to A to B to A relation as a product. And what else? We saw some examples, and now we can start new point in chapter 2. Okay, let's see. Okay, let's write the new title and continue with the page 3. Okay, page 3, we have new title as a relation. So relations. Okay, there is the definition. 2.1. Again, there is the two set A and B. A binary relation or simply relation from A to B is a subset of A product B. Okay, suppose R is a relation from A to B, then R is a set of ordered pairs where each first element comes from A, and each, we know that rule actually, second element comes from of course, B. So that is for each pair A is element set A and B is element of set B. Exactly one of the following is true. So what are those? And first one, A, B pair is element of R as a relation. A is R related to B, or we can write A, R, B. So there's a relation from A to B. And second, A, B pairs is not element of R relation, then we can say A is not R as a related to B. So we can show that R, A, capital R, not B. So any question for that definition? Okay, Emre said yes. So till now we saw some basic definition for the relation. Relations is not, simply from the product, and we will see some, different relation for sets. If there is the set A and set B, we will talk about some different relation also. But to explain the idea, product is really helpful for us. And let's continue. There is the, I think, example. It is really, easy and simple to get some idea. Okay, let's look at the example from your book. Okay, as a first one, A is equal, I'm sorry, set A has the element like 1, 2, and 3, and there is a set B. Set B has the element like X, Y, and Z, and there is relation with, A to B as a R. R has some pairs like 1 to Y, 1 to Y, 1 to Z, is a 1 to Z, and 3 to Y as a last pair. And we have as a R pair like that. Of course we can say R is a relation from A to B, right? Because first element of the pair is belong to set A, relation from A to B, because of R is a subset, of course, of A product B, right? But not all not all pairs inside of the R. That's why we said R is a subset of the A product B. So what we have inside of the R, what we have inside of the R, there is 1 to Y as a relation, right? 1 to Y relation we have 1 to Y, and we have inside of 1 to Z relation and 3 to as a Y relation according to that, explanation. But there is also some more because of the A product B, but we don't have as a 1 to X, right? 1 to X, and there is no 2 to X and 2 to Y and 2 to Z and 2 to 3 to X and 3 to Z. So we don't have that relation inside of the R. That's why we call R is a subset of the A product B. So this is the important, the domain of, so let's use different pen. The domain of R, so we defined R here. R is, which is the domain, as a 1 and 3. And the range is Y and Z. So this is important, and we will use for that explanation our future lecture part. And any question? Okay, I'm waiting the screen.